Hello, we are starting our seminar of IAU Commission H1, the local universe, and today our speaker is Javier Román from the Kapteyn Astronomical Institute, University of Groningen, Holland, and we will hear about a potential nuclear star cluster information. So you are welcome, Javier, to present your research.
Okay, thank you very much. So yes, in this talk, I want to show some peculiar properties that this galaxy has. And yes, just by chance, I've been analyzing this galaxy, and as I will show here, it has some funny properties or anomalies that may suggest the formation of a nuclear star cluster captured in the previous stages to its formation. So first of all, what are nuclear star clusters? Nuclear clusters are extremely compact stellar structures with a radius of around 10 parsec, located in the central regions of what is called nucleated galaxies. And this can be identified by, for example, photometric profiles, and they appear as a stellar overdensity in the central regions of the galaxies. The properties of nuclear clusters are different to globular clusters, and nuclear star clusters are not only located in the central regions of the galaxies, but they are much more massive. And you can see this in the left panel, comparing the luminosity of nuclear clusters versus globular clusters in galaxies in Virgo for galaxies at a given stellar mass. And they have also significant differences in their stellar populations. I will talk a bit on that later. But also, and importantly, not all galaxies have a nuclear star cluster. And here in the red panel, you can see the fraction of nucleated galaxies in function of their stellar mass. And you can see that the galaxies start to have nuclear star clusters that are around 10 to the 6 solar masses. They reach a maximum in the nucleation fraction around 10 to the 9. And for galaxies about 10 to the 12 approximately, galaxies lack of nuclear star clusters. And there are also additional correlations regarding the nuclear star clusters. And important for the discussion here, there are indications that the nucleated fraction on galaxies are also higher in higher density environments. Yeah, I will not enter in much detail here, but in general, the properties of the nuclear star cluster correlate strongly with the properties of the host galaxy in several aspects. So, how nuclear star clusters are formed? And here there are two different scenarios that are based in the observation of the properties of the nuclear star clusters and the host galaxy. The most widely established and also the first suggested mechanism for the formation of a nuclear star cluster is the coalescence or merging or fusion of globular clusters. In this scenario, some gravitational tidal perturbation will create the dynamical friction enough to break the orbits of some globulars that will fall to the center of the galaxy. And then they merge, forming the nuclear star cluster. In the other side, it is also known that the in situ star formation can put some mass into the nuclear cluster. Stellar population analysis shows sometimes some contribution of young population in the nuclear star clusters. These mechanisms are not, let's say, universal for all galaxies, but the coalescence of globular clusters seems to be more likely for galaxies below 10 to the 9 solar masses, and above the in situ star formation seems to be dominant. And a mixture of both mechanisms seems to be also frequent in galaxies. And this is shown very clearly with the analysis of the star formation history of a nuclear star cluster, showing these scenarios. So let's focus a bit in the globular cluster merging scenario. While observational evidence points clearly that the merging of globular clusters is a main channel for the formation of nuclear clusters, the thing is that still there is no direct observational evidence showing this process. And the point is that the simulations show that this process is expected to be extremely fast, of the order of some mega years. And the chances of catching a galaxy with a collapse of the globular clusters in the process are very low. So yeah, after this brief contest in nuclear star cluster, I will go to the analysis of this galaxy. And also to give a bit of a context to this galaxy, just to say that it is located in the peripheral regions of the Virgo cluster. Stellar mass is around 10 to the 9 solar masses. There is no sign of a star formation in the Sloan spectrum, no H1 detection, so no gas. And one of the peculiar properties of this galaxy that was in fact what catch my attention the first time is the presence of some weird shells, which is not expected in a galaxy of this mass. I don't know if you can see that in the image, that there are some shells or structures in the inner regions. Anyway, I will show later this in more detail better. And another thing that this is peculiar that is peculiar in this galaxy is that just by eye you can see a very high concentration of point sources that can be associated with globular clusters just in the inner region of the galaxy. And yes, I will show this better later. Here I show the photometric profiles of the galaxy. In the left panel, I show the photometric profile in the G band, and below the color profile in the G-R color. And the first thing to notice is that this galaxy has a blue core and a rather flat profile in the outer regions. I carry out a modeling of the galaxy, trying with a single surface model, which is the dashed line, and a double surface model, which is the black solid line. And the individual components of this double surface model are plotted as the blue and red lines. First of all, the color profile can be only explained by a double surface model, which is in which the central region is bluer and the outer region is redder. And the single surface model is unable to explain the redder outer regions of the galaxy. And we can also see in the red panel the residuals of subtraction in the profile of the galaxy to the single and to this double searching model. And as you can see, the double searching model has cleaner residuals, although with some fluctuations that I will show later that are to some structure that the galaxy has. So we can conclude that the morphology of the galaxy is better explained by two different stellar components with different and distinctive colors. Here I show the color composite images using G&R bands of the individual components of the double searching model, which is the one that explains better the galaxy. And the result of subtracting these models to the galaxy. And also I show here an enhanced image in fast color after binning the image, obtaining a much higher signal to noise of the residual subtracting this model. And as you can see, there are a lot of structures going on there, and you can see the presence of some strings or shells that are peculiar, and that suggests that indeed there is an interaction going on there. Indeed, the existence of two different components, stellar components, with distinctive colors and the presence of strings or shells indicate that this galaxy is likely the result of a dwarf merger. And in this scenario, the two different components of the modeling that have two different colors will be the remnants of the two galaxies that are not yet fully mixed. It is interesting also to check the literature if there is previous work supporting this statement of the dwarf merger. And the answer is yes. And work by Benitez Jambay using cosmological simulations showed that the expected outcome of dwarf mergers is the central concentration of the minor component, which tends to be bluer, surrounded by the redder and more massive component. And this is what we find in this galaxy. And also the work by Chun show that they studied the two blue core dwarfs in the bigger cluster, as it is the case of our galaxy. And by decomposing kinematically these dwarfs using spectroscopy, they showed that these are cases of recent dwarf mergers that are kinematically decoupled and are not yet fully mixed. So we can conclude that our galaxy is a very likely dwarf merger, which is already very obvious, given that we are seeing clear signs of interactions. And just to show also here the properties of both stellar components of the modeling, and in particular the masses, which will make a merger with a 1:5 mass ratio, stellar mass ratio. So the globulars. I carry out an analysis of the globular clusters candidates with the available photometry. And for that, I used the combination of GR and Z bands. And I've used this combination of bands in previous works and seems to be very efficient for selecting globular cluster candidates with a low contamination fraction. In this figure, I showed the detected globular clusters with green circles. And as you can see, there is a high concentration of point-like sources compatible with globular clusters in the galaxy. And I plot also the effective radius of the two stellar components or models that I showed previously. And I will talk more about the concentration of the globulars later. But first, I plot here in the red panel the color distribution of the selected globular clusters. The color space for the selection of the globulars is the gray region. The colors of both stellar components are shown with the red color for the main component and in blue for the minor component. And the colors of the globular cluster are shown as the green and yellow points, depending on where they are located, in which region of the effective radius of the galaxy. And I also plotted here the mean color of the globular cluster. And as you can see, the colors of the globulars are only compatible with the color of the main dominant component. So this shows that the globular clusters belong to the main radar component, stellar component, which is as expected, given that this is the dominant and a more massive stellar component of the merger. So let's talk now about the concentration of the globulars. And just by eye, you can see that the globular clusters are very concentrated in the inner region of the galaxy. Making the proper analysis, it shows that the half number radius, which is the radius at which half of the globular clusters are located, is very low. In particular, this is around 0.4 of the effective radius of the galaxy. You can notice that the concentration of the globulars can be of the order of the effective radius of the secondary stellar component. But I've shown previously that the colors of the globular cluster are only compatible with the red main component. So we should look to the red circle, which is the effective radius of the main component. So the very high concentration of the globulars seems to be real, and this is a strong anomaly because the typical values in the literature are of the order of the unity of this fraction between the half number radius versus the effective radius of the galaxies. And we have here around 0.4. Also to comment also that even assuming the effective radius of the galaxy as a whole, or just one single stellar component, this number for the concentration of the globulars remains similar. So this anomaly in the concentration of the globular clusters in the inner region of the galaxy is model independent. Whatever you use one or two stellar components, so seems to be real. This concentration of the globulars seems to be real. It is very interesting also to show the distribution of the globular clusters over the residual image after subtracting the model to appreciate the substructure that the galaxy has. And for that, I show an enhanced image of the residual, showing the most diffuse regions. And there is an interesting coincidence of the regions where the globular clusters are located over regions where positive flux is found. And this may suggest that the stellar material that is falling towards the center of the galaxy is also carrying the trajectories of these globular clusters. So let's put together what we have here. This galaxy has two anomalies. From one side, we have that this is a case of a dwarf-dwarf merger with two different stellar components. And on the other side, we see a very high concentration of globular clusters. A straightforward interpretation could be that the dynamical friction of the merger is causing the collapse of the globular clusters towards the center of the galaxy. And indeed, the previous works indicate that the soft tidal perturbations are enough to produce a collapse of the globular clusters and the formation of a nuclear star cluster. So this scenario is likely. Additionally, we can do the exercise of calculating the expected properties of this hypothetical nuclear star cluster produced assuming a merger of the globular clusters that are in the inner region of the galaxy. And by doing that, the luminosity of this hypothetical nuclear star cluster to be formed matches with the scaling relations between nuclear star cluster luminosity versus the stellar mass of the host galaxy. No? So everything matches well. And therefore, this galaxy is a candidate for a galaxy with a nuclear star cluster in the process of formation that has been induced by a dwarf merger, which is making the globulars to collapse towards the center of the galaxy. Yeah, we can further explore this scenario. And one of the things that we can think is how common are dwarf-dwarf mergers. If this particular galaxy is something special, or maybe we can think that the production of nuclear star clusters by mergers could be something more common. And the answer is that indeed dwarfs have frequent mergers in lambda CDM, so they are common. And on average, they suffer one major and one minor merger, which I think is interesting. Another thing that we can explore is what implications we'll have to assume that the dwarf merger is a viable channel for the production of nuclear star clusters. And I think this is an interesting point. In fact, one of the open questions in nuclear star clusters is to explain the environmental dependencies of the nucleation fraction. This is that the galaxies in denser environments tend to have a higher nucleation fraction. And if we assume that the dwarf mergers are able to produce nuclear star clusters, these environmental dependencies could have an explanation because indeed a higher environmental density will produce a higher merger fraction between dwarf galaxies. And I think this is something interesting. And we can be even more speculative. And we can think that the potential presence of gas in some of the merged components could promote in situ star formation in the stellar components of the produced nuclear star cluster. explaining the presence of young populations in the nucleus. No? As I say, this is of course now speculative, but I think it's interesting to take into account and to discuss within this result. No? So yes, with what we have, I wrote a short letter just pointing out the peculiar properties of this galaxy and the possibility that we could have here a nuclear star cluster potentially information. And this letter has been recently accepted. But before finishing, and I think I have more time, I would like to point out also that the future follow-up observations could be very interesting in this galaxy. First of all, the point source completeness. And our point source detection only allows us to detect around half of the expected globular clusters. In the top panels, I show the photometric errors for point source detection in all the 3 bands. And in the low panels, I show the luminosity function of the detected globular clusters candidates. The red vertical dashed line marks the expected peak of the luminosity function for a galaxy in Virgo. So as you can see, we are detecting around half of the globulars. To express the point like source detection here is not as straightforward, because for a globular cluster to be selected, we need the detection with a good signal to noise in all the 3 bands. And also the typical test of injecting and recovering sources is not straightforward here, because I use a residual image, and the impact of the residuals and some structures there in the photometry of point sources can be counted. But more or less, we can assume that the detection of the detection limit is around where we don't have more globulars, which matches approximately with the expected peak of the luminosity function, assuming that this galaxy is in Virgo, which seems to be the case, given that the galaxy has a radial velocity compatible with Virgo. No? But there is something strange here, and the globular cluster luminosity function is expected to be Gaussian, as you know. But here, for example, if you see the G band, we find an excess of breadth sources, and more or less the same for the rest of the bands. So a question that you can do is, do we have evidences that some globulars are already merged? And the answer is no. but the luminosity function seems a bit weird, and of course we don't have data enough to claim that, and I'm not claiming that in the paper. But I think it will be very interesting to do deeper and higher resolution photometric follow-up, just to check the shape of the luminosity function of the globular clusters, and to see the shape of the luminosity, to see if it's Gaussian, or if this excess that more or less we see here is real or not. No? And of course, something very interesting as well will be just to take radial velocities of all the globulars with spectroscopy, and to check the kinematics of the globular, to see if indeed they are in infall orbit or not. And this is going to be for future work. Also, of course, something interesting will be to do IFU spectroscopy on the galaxy, and also to check the kinematics of the stellar components of the galaxies, and to check what is going on there. No? Yes, that's all. Thank you. I will be happy to answer any question.
Thank you very much. Indeed, very interesting work. And thanks for inviting others to contribute to this type of work. So, who would like to ask a question? Yes, please, Yin.
Yeah, So thank you very much for the very interesting talk. So the globular clusters concentrated to the central part in this galaxy. How long does it take for them to settle into the very center? I mean, earlier in the talk, you mentioned about a few million years, but I think it's just too short for them to settle in. So in this particular case, how long does it take, do you think?
I'm not a specialist in that, but the literature that I've been checking, it suggests that through simulations, it could be of the order of some dozens of mega years, or even some hundreds of mega years. So this is the typical time scale for a system to collapse, no? To produce the merger.
So what is the rotation time scale at those radius, like half effective radius, for example? Because I think that already is longer than a few million years.
Yeah. I don't really know. It would be quite easy to do the calculations, no? But I assume that it should be more or less the same time scale of this simulation of this collapse towards the center. No? So yeah, probably of the order of some mega years or so.
Okay.
Do you know some examples where such globular clusters already are in the center?
I've been checking the literature of the studies showing the concentration of the globulars, and these are studies studying galaxies in Virgo, Fornax, and Coma. And I didn't find any example as this galaxy. This is quite a weird anomaly, and this is because that's why I think that this galaxy is special and something peculiar. And something that you can also think is if dwarf mergers are so common, why we don't find such an example, observational example of this process of collapsing. And checking the literature, the point is that in a virialized structure, the velocities are virialized and they are very fast, and the probability of encounters to merge dwarfs are lower. So the merger of dwarfs in the past, in a protocluster where the turbulence was higher, is higher. So you expect that this process is expected to be more common in the past. So maybe this is the answer because we are not seeing any other example as this galaxy, no? Because the mergers in the past were more common than right now. Just some divagations, no? To explain why this is something so peculiar, no?
Okay, and do you have some opinion about the Gaia Enceladus, this in foreign galaxy? What could be the nucleus of this galaxy? Can the cluster 1851 be the nucleus?
Oh, I have to say that I don't know this galaxy. I don't know the studies on this
This
galaxy.
is in foreign galaxy to our galaxy.
The Fornax galaxy.
This Gaia Enceladus.
I don't know. I cannot tell.
Or sausage. Somebody say also Gaia sausage. So
I don't know.
while investigating different streams, we find some structures in our galaxy, some in fallen dwarf galaxies in our galaxy, and there is discussion where is the nucleus of such galaxies. So some globular clusters are considered to be the nucleus or something like that.
Okay, interesting. I will check that.
Okay. So do we have more questions from participants?
Yeah, I missed the very basic information about the observational data sources for this your study. Which telescope?
This is the legacy survey, the CALS. survey with the
Ah,
Blanco telescope, I think.
I see. So do you have any chance to increase the resolution and the sensitivity in the future observations?
Yeah, in fact, it will be very interesting to do HST observations of the galaxy. No? It will be perfect. But in fact, we are going to try. We are going to try to with the HST. Subaru will also be perfect. The Subaru survey, but the galaxy is not in the footprint. But yes, indeed. For example, with GTC telescope in the Canary Islands, with a good thing, it will be also feasible to reach the whole luminosity function of the globulars. Yeah, the resolution is not great. It's around point something arcseconds.
I see. Okay, yeah, the target is very clear, so you should have a good chance to get observing time to improve the data.
Yeah.
Okay, thank you.
So you are welcome to make a new collaboration with Vaco concerning Subaru, I guess.
Yeah, Subaru will be very interesting indeed.
Okay, so thank you very much, Javier, for your interesting presentations, and we will see forward for your new discoveries and new research results. So thank you very much.